I have climbed up this great big glacial valley, and one of the things that I'm most excited to see here is something that has nothing to do with the modern day landscape. These beautiful rainbow shaped structures that you see here next to me are actually evidence of ancient life. I'm walking on snow here, so it's a little slippery, but there's a pretty spectacular layer of these things right here. Hey there, Callan Bentley from Piedmont, Virginia Community College. I'm up in Glacier National Park in Montana, and I've hiked up to Grinnell Glacier, and the glacier itself, of course, is spectacular, and I put up a video recently about that. But another thing that's really great about this location is these ancient microbial mats that are preserved as these dome-like structures, like this one here, right? And then this one here. So these are stromatolites, and they are fossils, but fossils of slime. So this is a macroscopic structure that forms when layers of photosynthetic microbes, probably cyanobacteria, were basically getting buried every day underneath a layer of calcite, and then they would grow up through that layer if they were to survive, and then live to photosynthesize another day. So they end up taking on these cool dome-like shapes that point upward. So they're a nice paleo up indicator, and that can be really handy if strata are really deformed. You can use that as a way of figuring out which way is up. The other thing that's really great about them is that they, basically are an indication of shallow water conditions, shallow depositional setting. There's a couple others here behind me. Those suckers. Because you can't photosynthesize unless the sun can reach the bottom of the sea. So they're a nice indication of waters that were shallow enough that sun could reach the bottom. There's a couple more here I'm going to show you. So I'm picking my way along. There's a couple right there. All right. Here's a couple that have kind of a neat shape, like a mushroom, kind of over-topped, like a muffin. These ones here are some of the taller ones that I've seen here in Glacier National Park. So there's my hand for sense of scale. But yeah, these guys really seem to grow upward at a greater rate than they were growing sideways. Elsewhere in the Helena Formation, we've got other cool primary sedimentary structures. One of them is shown here. Most of these little sand-sized grains in here are perfectly spherical, little concentrically zoned carbonate grains, and those are called ooids, and indicates also shallow water conditions at the time of deposition. Because to make ooids, you need to have conditions kind of like the modern day Bahamas, where the waves can reach down to the seafloor and kind of roll these little grains back and forth as calcite gets deposited all over their surface. Here's a neat block where you've got a layer of really big ooids at the bottom, and then in the middle you've got a fine-grained layer that has a couple of stromatolites doming upward, and then at the top you've got some smaller scale ooids. Spectacular little block. Another primary sedimentary structure that probably a lot of people will recognize are mud cracks or desiccation cracks. I guess in some of these rocks and glacier, there's some controversy as to the origin of these fracture sets, with some people arguing for desiccation, in other words, drying out in the open air, which is something that would be consistent with shallow water, which we already know was the case based on the ooids and the stromatolites. But other people have argued that it is a dewatering structure, some syneresis cracks. But in many cases, you'll find corroborating evidence that it was desiccation, like Here, I think these little dashes that you see, these little guys here and here, I think those are probably gypsum casts. And in many places, I've also seen halite casts here. Both gypsum and halite are evaporite minerals that form when seawater dries out. So I think it means that it's more likely that these are desiccation-related features. One more structure I'll mention that is kind of typical of the Helena Formation is this crazy pattern of veins that you'll see in some of these blocks. And this is called molar tooth structure. And it's a little bit enigmatic how it forms. We don't really know. There have been various hypotheses put forward, but it seems like there's no real consensus how this stuff forms. It only ever occurs in carbonate rocks, and it also seems to be limited to the Precambrian. So the usual rules by which geologists operate, the principle of uniformity, right? The idea that we use present day conditions to figure out how things must have played out in the past. That kind of doesn't apply when it comes to molar tooth structure because we don't have a modern day analog to go off of. So it makes it challenging. It's kind of like I guess you could say like an extinct primary sedimentary structure. Okay, so this is an example of another primary sedimentary structure. This is sort of a conglomerate that's made out of chunks of finer grained sediment. And that's what we call a mud chip rip-up class conglomerate. In this case, in a carbonate, in a limestone. But you know, that's a story basically of two energy levels at different times. First, low energy to deposit these fine-grained carbonate layers, and then a high energy event that ripped them up and tumbled them along, rounding their edges, and dumped them with other chunks. So it's kind of neat here because you can see some were originally fairly dark gray, and some were kind of light gray, and some were kind of orangey, and now they're all jumbled up together. Here's one of these layers that is one of these mud chip rip-up class dominated layers, kind of like a conglomerate, but in this case probably not made out of pre-existing chunks of limestone, but just sort of clots of limey mud that stuck together and then were ripped up and tumbled along and got these nice pleasantly rounded shapes.